see how we can use the physics, the phenomenon behind the total reflection, X-ray fluorescence spectroscopy, to analyze sample, to obtain both qualitative and quantitative data on our elemental composition of our sample. So I leave the screen to Ramon Fernandez Ruiz from Universidad Autónoma de Madrid. So welcome, Ramon, and the screen is all yours.
Hi, Ignacio. Thank you. Okay, thank you very much to all the people that I am looking that we are very much people, and this is very good. And only say that it's for me a pleasure to be here. It's a pleasure to be in a first time of something, and the first time of this special international summer school is very, very important. For me, it's very important. Okay, and after I am going to share my presentation. Okay, it's good. Okay, here. Okay, it's correct. You look perfect. Yeah.
Yes. Yeah, we can see everything.
Okay, good. Okay, good. Okay, the idea of this class talk, okay, conference is to give a qualitative and quantitative elemental analysis point of view from the TXRF techniques, okay? Because it's special, as you you know perfectly. But this question is very, very, very big and very long in time to go in depth and to explain correctly all the things. So we have only a limited time. So the idea goes to be, okay, centered in some ideas that for me are really important and that my experience say that are necessary take in consideration for a good practice of the TXRF, okay? Here you have my contact data. Please feel free of use to contact with me for any question related with this talk or with any other question related with TXRF or the science, general science. Of course, I won't recommend this book. It's the reference book of the TXRF from Reinhold Klockenkamper and Alex von Bollen. And I think that any professional of the TXRF so have this book in his office, in the lab, or in the bed sometimes. Okay, go to begin. The structure is very easy. As I has commented, I want a basic bombardment of basic concepts and key aspects about TXRF that I consider relevant for the whole understanding of the qualitative and quantitative practice, okay, of the TXRF. Of course, we are going to see general methods of quantitative analysis and also very much analytical application because, okay, along the week, I know that my college goes to develop this area extensively, okay? And finally, I like to do an experiment, and it's you see that I have in my background of my image here in the presentation a special image. It's the deposition of a sample, a water sample in particular, over a quartz reflector. You see, okay. Okay, the practice, the evaluation of the spectra goes to be of this sample, exactly of this sample, okay, with a real commercial software and with a real spectra of TXRF. This is the idea. Come on. Okay, the key aspect for me, the more important aspect, as I have commented, is based in the fact that the TXRF philosophy have two parts very well defined. The first part is the preparation, which is usually made in ionic way. This implies, from an analytical point of view, assure the homogeneity between the analytes, the atoms that we want evaluate, and in particular the internal standard, which is in ionic way too. Okay, but there is a critical point, that is the deposition step, where we transform this perfect homogeneity in something not so perfect, as you can see. Very beautiful, because the photographs are really beautiful, but not so homogeneous. And the lack of homogeneity is not very good related with the analytical parameters of the analytical results. So this is necessary, taking consideration always when one work with TXRF. Of course, if we think in the qualitative basis, of course, Professor Koichi and Peter have comment, explain very much things about, but for me, it's very beautiful, this animation. I like how the primary citation, eliminates an electron, and the energy is reductive rearrangement, and this adaptation of the energy induce the emission of characteristic secondary photons, which is the key of the qualitative basis of this atom, because only this atom can emit this photon, and this is the key aspect of the qualitative. Okay. Only comment that this is a dynamic aspect. It's continuously in production. If we have photons incoming to our sample, and if we have atoms that are able made transition, electronic transition. How much? Very much. In the order of characteristic time of 10 nanoseconds for its process, which imply very, very high flows of photons. And this is a very good characteristic if we are thinking in an analytical techniques, because a good analytical techniques is that that it's able of obtain a very high signal for a very low quantity of analyte, of atoms in this case. Okay. Good. Okay. Koichi also have comment about this, but yes, is the key of the qualitative identification. Here there is a real spectra of cobalt and gold signal. Here we can see the K lines of the cobalt and the L lines of the gold atoms. Okay. Here we can see the K lines, the L lines, and M lines usual for a model of atom more robust. Only a particularity is this fact we obtain only 2 peaks experimentally with our detector, K alpha and K beta, but theoretically there is much transition, K alpha 1 and K alpha 2, for example, and K beta also. Here there is 2 transition, K beta 1, K beta 2, but here we have only 1 peak. Why? Because they are very, very near, and then we are looking the contribution of both. Okay, there is an overlapping of each one of the transition, as you well know, I'm sure. This process is the same for the L lines, okay, but here there is very much possibilities, and it's a little más complex. Okay, this has been comment. I think that for Koichi, it's enough, the different notation. Mostly love also has been comment for Koichi, I remember, but okay, only comment that this is of course the key of the qualitative analysis by TXRF or XRF, and that it's based in this relation found in its doctoral dissertation by Mosley, before of the, okay, no, okay, he was killed in the First War, you remember? It's a very bad remember, I don't like, okay. He saw that the relation between the energy of the emitted photon and the atomic number, that is the element of the periodic table, follow each one of the transition follow parabolic functions, okay, of this type. In this case, for any atomic number, that is any element, if we trace a linear, a vertical linear, the contact, okay, represent the energies where we are going to form, okay, the peaks associated to this atom. Oh yes, this is the method to obtain the actual, okay, the general database of position, energy position and transition. Okay, good. From the quantitative, the more important is the concept of the quantum yield that I remember that Peter Kersheimer has commented something about. Okay, only comment that it's necessary sum the quantum yield and the quantic concept of the phenomena of the fluorescence with the fundamental parameters, the apparition of the second or higher interaction order, also the absorption, okay, and combine for can to describe, okay, a quantitative way of the general X-ray fluorescence. Okay, here I only want to comment that in all the case, for all the atoms, we are going to find always that the intensities of the K lines are always higher than the L lines and higher than the N lines for all the atoms. And this is a good aspect, okay? Because always follow this sequence. More things. The question of the matrix. If we have not very much atom in the travel of the photons from our X-ray tube to our sample, and from the side atom to the detector, okay, this appears a linearity from the number of atoms and the photons obtained. That is similar to the geometry that we can obtain in TXRF. But if the travel are higher, is the case of the traditional fluorescence, the probabilities of that appears second or third or higher iteration are very probable, and this imply the loss of the linearity in any case. So it's a very hard problem from the physical and from the mathematical point of view that is solved by the Sermon equation. Okay. When we are looking at TXRF spectra or an XRF, usually we are looking three main physical phenomena. There is much more, of course. But of course, we are going to see the fluorescence phenomena. We are going to see inelastic collision, that is Rayleigh phenomena, and we are going to see Compton phenomena, okay? Inelastic scattering of the incoming X-ray from our source. Yeah, this is true. This is a real spectra of TXRF, a well-known spectra, I think, because I am sure that very much people of the present audience know perfectly this spectra. It's the well-known Merck 4 that it's composed by I remember that 24 elements with the same concentration, 1000 ppm, and we can find, you can see, all the fluorescence, K lines, L lines, even M lines, And the Rayleigh associated to the source that we are using for citing this sample is molybdenum K-alpha, and the associated Compton to this Rayleigh scattering. Okay. Only remember this question that is from an analytical point of view, all the key is the amplification that the spatial region, okay, of where the X-ray standing wave is generated is produced. That is, if the intensity of the electromagnetic wave incident over or reflector have an intensity of 1, the intensity generated for a constructive interference with the reflected wave, it's up to 4. Okay, so this region is an amplificator of intensity. So the atoms that were inside goes to be amplified with a very high effectivity. And this is the special key one of the TXRF. And this is a gift that I want to give you. This is other vision of the TXRF. The TXRF is the convolution of very much aspect. You know that the critical angle, the angle of incidence is very, very important. Yes, it's very important. Here you can see very, very good. That is the combination of the usual spectra, intensity with energy, for different incident angles, okay? In particular, for this sample, that is a distribution of titanium oxide nanoparticles, okay? We can see, for example, here it's these mountains. This is these mountains. Now we have not lines. Now we have mountains surface, okay? It's associated to the titanium K-alpha, and this to the titanium K-beta, and we can see that for this is angle, okay? For angle at this level, this line, okay, it's not very good observed, but understand me. In the peak of the mountain is the optimum condition of maximum excitation of the atoms present in this sample. Okay, okay, it's only a gift. Good. Now, if we introduce a sample in this special region, we are going to obtain an improved excitation intensity of the elements present. And goes to varies from 2 up to 4, depending on the geometry, okay, of the depositions. But simultaneously, as Peter has commented to, the background goes from the, in this case, quartz or silicon, if it's a buffer, okay, goes to 0 practically, very, very, very low. If we combine both effects, we obtain the optimum relation for an analytical techniques. That is, considering the measuring angle, that never is the critical angle. Usually the measuring angle in TXRF, it's around 70% the critical angle, okay? In this position, you can see that the intensity is maximum and the background is minimum. It's the optimum signal to noise ratio. Okay, and what implied this? Implied very much thing from an analytical point of view. Implied that the sensitivities for all the elements are always improved. And of course, the detection limits are very, very low. Okay, in particular, for classic instruments, the absolute detection limits are in the order of picograms. That is in the order of ppbs. But okay, the actual results obtained with new generation spectrometer allow to obtain the detection limit down of the picograms in the fermigrams region and down to the ppb. In fact, this detection limit depends of very much thing. In the experiment, I won't show you the results obtained for this water, because remember this image of the detection limit, because okay, we are going to find okay, similarities and a strong difference. Good. I am not going to explain again the detection limit because Peter Kastamer has commented to you. Only comment here the Poisson statistic applied to the counting of all detector. But yes, I like to add an additional consideration. At this the time. You can see this experiment. This is a sample of, in particular, of spleen, digested, okay, where for an element, in particular phosphor, I have evaluate the concentration to very different time. You can see the time from 50 seconds up to 1050 seconds. The range in time is okay, high. You can see that the nominal concentration is constant within the statistical variation in this case. But if we evaluate the detection limit time for each one of the spectra, you can see that it's, well, follow in a perfect way this equation, that is the inverse of the root square of the time. And wow, it's perfect. And really, the correlation is of 3/9. Okay, and it's very high. This allows us to optimize the acquisition time of our spectra. In this case, it's clear that for times from 500 to 1000 seconds, the limit of detection, okay, no varies significantly. Okay, and then this region can be considered as adequate to obtain the best results with respect to this analytical parameter for this sample. Okay, only for your consideration. Okay, then if now one analyze quantitatively, as I have commented previously, in a general way, considering general X-ray fluorescence, we need to use this very hard equation of Sherman, okay, where all the geometrical, all the assertion, all the second iteration even, or okay, all the parameters, physical and chemical parameters are inside. If we now apply a monochromatic approximation, because we with our spectrometer usually apply monochromatic radiation, and apply also the geometrical approximation given by the TXRF geometry, that is that the incident angle is practically zero and the out angle is around 90 degrees, we obtain, okay, important simplification of the Sherman equation. And if additionally we apply the simple approximation, that is how usually we work with TXRF, we obtain this very beautiful equation that implies a linear relation between each one of the intensities. Sorry. Okay, and each one of the concentration of the elements present in those samples. Okay, and this is this linearity is the more relevant analytical characteristic of the TXRF, and it's okay, the key also. of the TXRF. Okay, this approximation from a mathematical point of view for the question of the school are here present. This is the geometrical approximation and the implication with respect to the general absorption factor, and the thin-fold approximation and the implication with respect to geometrical approximation, that is convert this factor in a factor 1, that is the absorption, in this case, the Chaper. Okay. And this translates to the practical way in the classical work of Klockenkamper and von Bohlen from 1989 year, where they apply this physical condition to three different matrices, from heavy matrix, metallic smears, medium density, mineral powders, and light matrix, organic tissues. Okay, and obtain measure the thickness and mass limit, the maximum limit of mass that one should add to our reflector to obtain, to accomplish the linear behavior of the TXRF previously defined. Okay, and you can see here graphically and here in number that these values are very low. Very low. For example, for mineral powders, we are speaking of thickness around 50 nanometers. It's very small thickness, and mass no more than 5 micrograms. Okay. With this, I won't say take care, because linearity is lost very quick, and the loss of the linearity can be translated in alteration, okay, in the quantification by TXRF. Here you have an example where, in this case, was evaluate the linearity of magnetic nanoparticles, okay, evaluating the signal of iron with respect to the mass deposited on the reflector. And you can see that from 0 to, around, 2.5 micrograms, that is this region, the behavior is really linear. But for higher mass, you can see how the slope varies very significantly, and the linearity is clearly lost. Okay, 2.1, and we are speaking about magnetic, iron oxide. Yeah, okay, this is similar to the previous mineral powder, lower to 5 micrograms. Okay, we are into outer region. Okay. No, good. Okay, and now we need to obtain our experimental relative sensitivities, of course, and how. The process usually, this is a very good method. The more important is to obtain, to have very good standard, really, single standard or multi-standard that you can combine to obtain a good sequence of atomic number, okay, of well-known concentration. For example, this, obtain deposit, obtain the spectra, obtain the distribution of element, in this case, for example, to evaluate the sensitivities of the K-lines in the molybdenum calcitation, with molybdenum calcitation, and elect one of them as a reference. In our case, for example, cobalt was normalized to 1, as you can see, and the sensitivity we normalize also to 1. Okay, so we are obtaining the relative sensitivities versus cobalt, really. The concentration are well known because we have a very good standard, and for this are important. And the intensities are extracted and measured. We obtain 10 the single points, you can see, and all the other atomic number can be obtained by polynomial interpolation. And then we can to have the sensitivity factor of all the elements in the region of measurement. Now we are going to measure the classic method, the method that is universal for TXRF if all the conditions are complied. And it's good for any sample in solution or even in suspension, is this, the internal standard. It's very easy. And use the linearity, okay? This is a very linear relation between the parameters of the internal standard and the analytes of all the elements detected, observed in the spectra that we are analyzing. And it's very easy. Take an aliquot of our sample, add a perfect volume of our standard of very well known concentration, homogenization, taking and transform in a deposit and analyzing, okay, measuring the intensities of the elements present. In this case, for example, if we have used gallium as internal standard, and we have add 60 ppm for a sample, we know the sensitivities we have calculated previously. Okay, we have calculated, and only it's necessary to obtain the intensity ratios if we know all the other parameters to evaluate the concentration of all the elements that we have in our spectra. If our sample is more complicated, if we have problems with the matrix, we can use this standard method, classic method 2 for any analytical techniques, even for TXRF, that is the standardization method, and is based in measure our sample directly, okay, and add a now concentration of the analyte that we want to evaluate. And then, by mean interpolation, we can measure the concentration of this analyte. And this is interesting because it's allow avoiding matrix effect. So if one have idea that the sample is especially complicated, okay, one can use both methods for the same element and compare. The solution should be the same. No, this is a very good auto-validation strategy that is okay. It's necessary sometimes used. And the more easy application of the TXRF is the evaluation of mass ratios, the fingerprint, that is for evaluation of stoichiometry or trend studies. And it's so easy as transfer to over the reflector and fizz of a reflector, a liquid, a particle, okay, the sample, evaluate the intensities, and apply the linear equation to estimate the, in this case, mass ratios between the signal found in the spectra. In this case, for example, it's a special material of a solid solution, very, very difficult of solution in acid digestion, because there is problems with indium, evaporation, selenium. It's a complex of sample. Well, okay, go to analyze directly. So we only need to obtain the spectra, normalize each one of the signals, in this case to copper, the central element, was normalized to 100 relative mass units in this case, and the mass of indium and mass of selenium were evaluated in comparison. So with this data, relative mass really can be calculated the atomical proportion, and then as consequence the geometric coefficient that were the objective in this investigation. Okay. Good. Okay. This question is very, very important for the things that I am coming to you. When I say that the deposition is the key, is for this for this question. This question is that this inhomogeneity, okay, so it complies for the sample and for the internal standard. If this inhomogeneity is not complies for both simultaneously, okay, we can to have problem. Okay, this is the idea that I like to transfer to you. For example, from an spatial distribution, in this case, these are nanoparticles of iron oxide. You can see the iron distribution, and you can see the internal standard distribution in this case. Okay, spatially are overlaid. Good, because if there is absorption, appears this absorption for both signal, not only for the iron signal. Okay, this is the idea. After this characteristic, the internal standard should follow the safe at microscopical point of view, or macroscopical, but morphologically should follow the same safe. That is, in practice, if we have particles, that is this line in this angle scale, okay, our standard should be also nanoparticles, cannot be as a monolayer. That is the idea. This structure, okay, sure that we have lost the linearity and sensibility relation that we previously have found. Okay, the relation between the intensity of the internal standard with respect to any element, because the safe and the intensity response are different. Okay, so it's critical. So take care. Only want to say this. Really, this is not usual, but it's necessary. Always take in consideration. Okay, only this case, for example, a very easy question. Okay, we are going to analyze Coca-Cola, Coke beverage. Well, very easy, no problem. We eliminate the carbon dioxide or to eliminate the bubbles of gas, and it's okay. It's a liquid. Okay, no problem. A standard internal addition. No problem. Okay, no problem. Sorry. Good. We are going to check in a direct way, and with time you can see this morphology, microscopical morphology. It's a crust really of sugar, of saccharose in particular. Okay. But this have implication. With time, you can see the black concentration results for this sample with this crust. And now the same sample of high pressure and high temperature microwave, we break completely all the sugar, and then we obtain okay, very thin film of the metals present, and we obtain now these results for the same elements and for the same compounds. Okay, what is important here? That the deposition is important, okay? And also that the quality of the results depend of the sample preparation. In this case, if we only made a very simple preparation, our results goes to be not so good. But if we prepare from the first moment by a complete gestion, okay, minimizing the matrix possible effect, the possible absorption, the micro-run deposit, the depositate over the surface, okay, it's possible that we can obtain very good results. It's okay, only as conclusion of this. Okay. Only comment here that for a deposition so no homogeneous as this sample, it's very difficult to obtain results. But this is not certain because we can obtain good results applying statistic, okay, over this deposition. How? Applying different strategies of measuring, okay. Only in this case, for a sample of hair digested in Medioneolithic tube, it was this sample, or I think, you can see here three different evaluation of the reproducibility, okay, of the measurement. In this case, the same sample was measured in the same position, okay, with respect to the X-ray incidence. So, in the same lane, okay, we are measuring 3 times. And at this condition, we obtain a repetibility of 1.6%. Very low, it's very good results. But the same sample, if now we measure one at this angle, other at this angle, other at this angle, that is 0, 120 degrees and 240 degrees, for the same sample, we obtain reproducibility in this case by rotation of 3.6%. And if we evaluate the reproducibility in a conventional way, that is 3 different deposition, 3 Gaussian measuring, we obtain a reproducibility of 6.56. So yes, it's important, the inhomogeneity, yes, but we can evaluate, we have different strategies to evaluate the uncertainties, in particular in this case of deposition. From the point of the quantitative point, quantitative data, you can see in this representation that for all the elements evaluate, okay, there is not significant difference for each one of the evaluation. Nominal values are the same within the error bars, you can see, okay? But the unique difference is how many error we want to evaluate, okay? So in this case, even for a sample so difficult as this, okay, TXRF can work properly, okay? This is the other idea. And now I like to do this experiment. This experiment is related with this deposition, is the deposition that I have here in my background. And it's really this standard, okay? It's a river water standard from the National Research Council of Canada. We're taking, in this case, 50 microliters of this reference material speaked with 100 ppb, okay, of gallium as internal standard, was dried, okay, and analyzed with our Pico-Force instrument. Okay, now I'm going to Okay, I have open here. Yeah, here is the. Okay, I am going to open. In particular, this spectra, 50 microliters. Okay. Okay, this is the spectra software that our S2 picophores have to our disposition. Okay, in the offline mode. No. Okay, I am going to eliminate all. Okay, I am going to use this standard method. Yes. Okay. Okay, and here we have, I am going to eliminate this. I'm going to, okay, here we have the complete spectra, okay, and the real spectra with the real noise, with the real problems of detection limits, with all the real aspect that one can find in for this sample in particular. Okay, we know that we are using gallium. Gallium, it's here. Okay, then I am going to mark. This is the periodic table. Okay, and this is the tool for qualitative evaluation of the spectra that this system have. Okay, also scandium, because we have used a scandium, both elements, gallium and scandium. Okay, and okay. We are going to see, for example, now I am going to positioning. Okay, perhaps it's more interesting this. Okay, okay. Yeah, that's more. Oh yeah, this is possible. He proposed silicon. Oh yes, it's interesting. Not only propose the element, also propose the safe of the peak, which is very helpful for the interpretation. Now I am positioning this peak. Yes, sulfur. Okay, and the explanation of both peaks are correct. Okay. Yeah, chlorine. We have very much, but this is argon. Sure. Okay, now it's good. Evaluate the chlorine. Yes, there is chlorine. Argon is not good to evaluate, but if now we apply potassium, now it's good to evaluate. Okay, this is a problem of integration because simultaneously it's identify element and introducing a profile and minimizing the area. Okay, no problem. But there is potassium, I'm sure. There is calcium, sure. What more? Oh yes, there is barium. Here the combination by this and this presence and this. Okay, perfect. Manganese, iron, yes, iron, manganese, perfect. What is this? Nickel is not good, but yes, perfect. Nickel, copper. And this is thin, yeah, very good. Now it's good to the convolution. This is gallium, Ki alpha, Ki beta, very good. And this is bromide.
Add 2 minutes.
2 minutes.
Yeah.
Okay, sorry. sorry. Okay, okay. I'll only use this. Yeah. Okay, now. Okay, with this quick qualitative characterization, we can see Okay, identify directly all these elements that you can see in the spectrum. Okay, all the elements that are signed in the periodic table. But additionally, of how we have introduced the concentration and the quantity of our internal standard, directly can in this case apply and quantify the results. But you can see. And now this is in relation with something that I have commented previously. In this case, we are working in ppb level, okay? But you can see, for example, for nickel, we are obtaining ppt level. We are measuring in ppt level. But if you consider, sorry, I'm going to eliminate. If you consider the detection limit for all these elements from manganese to strontium, we are in the PPT level, okay? Why? Because this matrix is special. It's a very clean river water, okay? And the difference between the maximum and minimum concentration of the elements are, okay, in the range of the TXRF. For example, the maximum concentration in this case is calcium and is 10.5 ppm. In this case, okay? Okay, we can compare with the certificate, but okay, I think that is not necessary, but it's only for your okay, because I like. Yeah, this is the reference. Okay. For example, for particularly interesting, arsenic, 4013 PPT certificate, okay? Arsenic, what is? Oh my God, it's not.
You can put in the convolution.
Sorry.
Put in the convolution, arsenic.
No, yeah, I have not seen. Oh my God, the third time. But I remember nickel, 4088. Let's see. Nickel, 4076. Okay. It's very interesting, this data. We are measuring with a certificate material PPT level, only as common, only for think about. And with this is for me enough. This is my objective, that really it's centered in common with you that it's necessary, it's totally necessary, take care with the deposition. It's a factor very, very important, okay? Because the analytical results obtained by TXRF depend in a great measure of this deposition only. Thank you very much.
Okay, thank you, Ramon. We know that this is very wide topic. So the problem of the matrix, and however, we have a lot of questions connected with all this big problem.
I prefer.
And I invite the people to ask questions by themselves. I'm reading some questions by Maripaz, if she wants to ask the question directly.
Oh, yes.
This is perfect. Maripaz? No, okay. Anyway, she's after all, getting a thin layer and best condition, etc. How you can choose the proper amount of internal standard in a complex and unknown sample?
Okay, it's easy. Okay, the magic, the best rule to let Maripaz the standard internal is, first, we have not in our sample. Okay, this is obvious, but it's necessary to evaluate that the range of intensity of the signal, not concentration of the signal, because there is a strong variation, was in the middle of the maximum and minimum of the lines that you are evaluating. This is optimum. Then you are okay, near of the low intensity and okay, near of the high intensity. This is the idea, general idea. Okay, in practice sometimes it's difficult, but okay, this is the intention, or solving the intention. But in any case, Maripaz, okay, contact with me.
Ignacio, you are muted. Microphone.
Sorry? No te oigo.
Cannot hear Ignacio. Ignacio, we cannot hear you.
No? I have looking very much in the chat, very much in the chat. It's very good, but okay, you hear me? You hear me?
Yes, we don't hear Ignacio.
Okay.
So please, Ramon, if you can read yourself the questions and maybe answer, please.
Qué buena pregunta. Well, it's very good question. This I like very much. Okay, Julimar, comment something about Julimar. Are you present? Okay, if you are present, you can connect your camera and we can see your face. But okay, in any case, it's a very good question. Okay, it's necessary that you made a very hard qualitative evaluation before. Okay, you need to analyze high quantities out of the thin film condition. Don't worry, but you need to are sure of the elements that you want to measure. Okay, and then this is a first step, and then you have the first image, the first fingerprint of your sample that is in the noise as you comment, and then you have criteria to a good relation, okay, of the standard internal, and then quantify if it's possible. Okay, more. Graciela. Hi, Graciela. How are you? How can I get the sensitivity of an element? Oh, measuring, Graciela. Measuring. What sensitivity do you want to obtain, Graciela? The absolute sensitivity? Or the relative sensitivity. Relative sensitivity is very easy to obtain, as you see in this presentation. It's a little more complex if you want the absolute sensitivity of an element. Okay, for this is necessary prepare a linear regression with different concentration and evaluate this absolute sensitivity as the slope, okay, of the regression, linear regression. Okay.
Sorry, Ramon. I'm taking
same
the chair because Ignacio has some technical problems. Please, if we can just reply to one other question, because maybe you can reply later to each. But there are really many questions. We have to close.
There is question, sorry, there is problem with the sound of Ignacio, with my sound?
No, with Ignacio. So that's why I took over. So with you, it's perfect. So I just kindly ask you to reply just one last question, maybe this one from Salvatore Tripoli. Good morning, Dr. Fernandez. Is it possible by TXRF to carry out a quantitative depth profiling analysis on multi-layered film?
Yes, of course. Along this week, Salvatore, you are going to see. There is the next application of the TXRF is the variation of the angle of incidence, as I have commented in one of the presentation, only as a gift, because really it's not my specialty. But I'm sure that we are going to give to speak about the grazing incident application, and then is where depth profiling can be made. We are going to do, but not today, along this week.
Okay, thank you very much, Ramon. I just kindly ask you to reply separately to all these other questions, if possible, or maybe the participants can contact you privately on your email for other questions. But I'm sure that with the following, the next presentation, the next year will give answer to your questions. So I think we have, yes.
Okay,
please.
okay. No. It's possible that you send me these questions.
Yeah, you can read it in the chat, and
okay.
People can write you directly. I'm back now.
Yeah. So. No, but okay. No, it's good.
Okay. So thank you very much, Ramon, and thank you to all the speakers today. We are